Time before time. Big Bang and inflation. When we step outside on a clear night and look up, we are looking at light that has traveled for unimaginable stretches of time. Stars that wink back at us may be hundreds or thousands of years old. Their photons launched long before pyramids rose on Earth. Galaxies, faint smudges to the eye, but spirals of brilliance through telescopes, carry light that began its journey millions of years ago. But beyond even these, stretched thin across the entire sky, there is another kind of light, far older, far stranger. It is not light from stars or even galaxies. It is the light of creation itself. This light is the cosmic microwave background, the faint afterglow of the Big Bang. Discovered accidentally in 1965 by two radio engineers, Arno Penzias and Robert Wilson, it first appeared as an irritating hiss in their antenna, like static that would not go away. What they had stumbled on was nothing less than the cooled echo of the universe's birth, radiation left over from when the cosmos was only 380,000 years old. For cosmologists, it was as if the universe itself had left behind a baby picture. Grainy, yes, but full of clues about its origins. The CMB became the Rosetta Stone of cosmology. Hidden in its faint ripples was a record of how the universe began, how matter clumped, and how the great tapestry of galaxies was seeded. To study it was to time travel to an era before stars, before atoms had even formed, when the universe was still glowing with its primordial heat. But the CMB is not a simple story. At first it looked smooth, so uniform across the sky that it seemed to tell us very little. Yet with sharper eyes and better instruments, scientists began to detect tiny variations, hot and cold spots in the glow. These were the fingerprints of the very first fluctuations, imprinted by processes we still struggle to understand. If we could decode them, we might be able to push back beyond the Big Bang itself, into a realm of time before time. The effort to map the cosmic afterglow began with COBE in 1989. COBE was a modest satellite by today's standards, but its achievement was revolutionary. It confirmed that the microwave background was a perfect blackbody spectrum, exactly as the Big Bang theory predicted. It also revealed the first evidence of ripples, a cosmic murmur barely 1 part in 100,000. For this, John Mather and George Smoot won the Nobel Prize. And cosmology moved from speculation to precision science. Yet COBE's map was fuzzy, like a child's sketch. To truly see the universe's baby picture, sharper instruments were needed. Enter the Wilkinson Microwave Anisotropy Probe, WMAP, in 2001. With WMAP, the universe suddenly came into focus. Its maps, released in 2003 and updated for a decade, showed the microwave sky in exquisite detail. The data confirmed that the universe is 13.7 billion years old, geometrically flat, and dominated not by visible matter but by the unseen forces of dark matter and dark energy. It was as if WMAP handed cosmology a new compass, pointing with precision toward the shape and fate of the universe. But the real watershed came in 2013, with the European Space Agency's Planck satellite. Planck's instruments captured the CMB in the sharpest detail ever achieved, resolving its subtle patterns like a master painter, revealing fine brush strokes. Suddenly, the primordial sky was not a vague blur, but a rich texture, a cosmic quilt of hot and cold patches stretching across the heavens. Each patch was a seed of future structure, destined to become a galaxy or a void. The Planck map told a story that was at once reassuring and unsettling. On one hand, it confirmed the Big Bang model with astonishing precision. The universe was about 13.8 billion years old, and the recipe for its contents was clear. A dash of ordinary matter, a larger portion of dark matter, and a dominant mysterious ingredient, dark energy. On the other hand, Planck raised profound questions. Why did some regions of the sky show anomalies, like a strange cold spot, larger than expected? Why was the universe's geometry so perfectly flat, as if balanced on a knife's edge? More than that, Planck's results confirmed something deeper. The tiny fluctuations in the microwave sky were not random noise. They were structured, with patterns that pointed to an astonishing conclusion: that the universe had undergone a burst of violent expansion in its first fractions of a second. This was the theory of inflation, and Planck's maps became its strongest evidence yet. When the Planck satellite delivered its results in 2013, cosmology crossed a threshold. For the first time, we could say not only that the Big Bang happened, but that we knew its recipe with remarkable precision. The universe was no longer a mystery box. It was a measured pie chart. Planck revealed that only about 5% of the cosmos consists of ordinary matter, the atoms that make up stars, planets, and people. Roughly a quarter is dark matter, invisible yet holding galaxies together. The remaining two-thirds is dark energy, the enigmatic force accelerating cosmic expansion. For many, this was the most humbling revelation. Everything we see, every planet, every galaxy, every glowing star, is just a thin glaze on a vast, invisible cake. But the true triumph of Planck was its portrait of the early universe. Its high-resolution map of the cosmic microwave background showed ripples across the entire sky, like the grain in ancient wood. These ripples weren't random. They reflected precise acoustic vibrations, sound waves rippling through the hot plasma of the infant cosmos. By measuring their spacing and intensity, cosmologists could trace how matter and radiation interacted in the first 380,000 years. The peaks and troughs in this cosmic music lined up almost perfectly with the predictions of a universe governed by Einstein's equations and seeded by quantum fluctuations. And yet, woven into this triumph were puzzles. The map revealed odd asymmetries, like one hemisphere of the sky being slightly smoother than the other. There was also the famous cold spot, a region larger and colder than expected, perhaps just statistical chance, or perhaps a window into new physics. Planck confirmed the universe's remarkable flatness, but that very flatness was troubling. Why should space be so precisely balanced, like a ruler stretched to infinity without the slightest curve? Such mysteries pointed toward inflation. Planck's results didn't prove it outright, but they set the stage. The universe's flatness, its uniformity across vast distances, the specific distribution of fluctuations, all were just what inflation had predicted decades before. The word inflation usually brings to mind rising prices, but in cosmology it means something even more dramatic: the universe itself ballooning at a furious pace in its first moments. Imagine the entire observable cosmos, billions of light years across, once smaller than a proton, and then swelling in an instant to cosmic scales. This is inflation, a brief but overwhelming expansion, perhaps lasting only a fraction of a second, but long enough to change everything. Inflation was proposed in the early 1980s to solve three nagging puzzles. The first was the horizon problem. Why is the universe so uniform? Regions of the cosmic microwave background separated by billions of light years are nearly the same temperature, even though under normal expansion they could never have been in contact to even out. Inflation solves this by saying they once were neighbors, compressed together before expansion stretched them apart. The second was the flatness problem. General relativity allows the universe to be curved like a sphere or saddle, yet Planck showed it is astonishingly flat. Without inflation, this balance would be unnatural, like balancing a pencil on its tip. But inflation flattens space automatically, like stretching a balloon so wide that its surface seems flat. The third was the monopole problem, a relic of particle physics. Some early theories predicted exotic heavy particles that should still fill the cosmos, yet none are observed. Inflation dilutes them away, sweeping them beyond the visible horizon. But inflation did more than solve problems. It provided a mechanism for creation. During inflation, tiny quantum fluctuations, random jitters in fields at the smallest scales, were stretched to cosmic size. These fluctuations became the seeds of galaxies, clusters, and the web-like structure of the universe. In other words, the universe's largest structures grew from the smallest conceivable origins, amplified by a burst of expansion. The elegance of inflation captured cosmologists' imaginations. It explained the Big Bang's smoothness and its wrinkles. It accounted for the flatness and scale of the cosmos. And it made a testable prediction. The fluctuations should follow a nearly scale invariant spectrum, meaning they look similar across many sizes. Both WMAP and Planck confirmed this with exquisite precision. Still, inflation raises questions as deep as those it answers. What drove it? A mysterious inflaton field is often invoked, but its nature remains unknown. Why did inflation end, allowing the universe to settle into normal expansion? And, perhaps most provocative, if inflation occurred once, might it occur again and again in other regions, birthing countless universes in a grand multiverse? Inflation is no longer just a fix to cosmological puzzles. It has become the dominant story of cosmic beginnings, and yet it is not the final word. For all its successes, the hunt is still on for the ultimate evidence. A direct fingerprint from those first fractions of a second, written not in light, but in gravity itself. If inflation really happened, it should have left a smoking gun. During that furious expansion, space itself was stretched so violently that it should have stirred the fabric of reality, sending out gravitational waves, ripples in space-time. Unlike the ripples detected by LIGO from colliding black holes, these would be primordial, born at the dawn of time. But how could we ever detect such ancient whispers? The answer lies once again in the cosmic microwave background. When light was released 380,000 years after the Big Bang, it carried with it not just the temperature fluctuations we see as hot and cold spots, but also patterns of polarization, subtle twists in the light's orientation. Certain swirling patterns, called B modes, could be caused only by primordial gravitational waves. If we found them, it would be direct proof of inflation. The search began in earnest in the icy wilderness of Antarctica. The South Pole, with its dry air and long nights, provides some of the clearest skies on Earth. There, experiments like the background imaging of cosmic extragalactic polarization, BICEP telescope and its successors, were designed to peer into the CMB's polarization with unmatched sensitivity. In 2014, the world of cosmology buzzed with excitement. The BICEP2 team announced that they had found it, a clear signal of primordial B modes, a long-sought fingerprint of inflation. The headlines were dramatic. Proof of the Big Bang. First glimpse of the multiverse. Einstein vindicated again. But science is a careful process. Soon, another explanation emerged. The polarized signal BICEP2 had seen was real, but it likely came not from the early universe, but from dust in our own galaxy. Interstellar dust grains align with magnetic fields, and their emission can mimic the very pattern cosmologists were hunting. When data from the Planck satellite was combined with BICEP2, the signal faded into uncertainty. The smoking gun had dissolved into cosmic smoke. Yet the disappointment did not end the hunt. It sharpened it. The search for primordial B modes continues today with even more precise instruments, such as the Bicep 3 and Keck array upgrades, as well as the South Pole telescope. Each is pushing the sensitivity deeper, peeling away the veil of galactic dust to reach the pristine cosmic signal beneath. It is a chase as much philosophical as scientific. If we find those primordial ripples, we confirm that inflation is more than an elegant idea. It is a historical fact. If we fail to find them, we may be forced to consider alternatives. Either way, the pursuit is reshaping our picture of the first instant of time. Inflation may be the dominant model, but it is not the only story of cosmic origins. The deeper cosmologists probe into the moment before the Big Bang, the more they realize that multiple paths may exist, and all of them touch on the strange rules of quantum physics. One alternative is the bouncing universe. Instead of beginning from a singularity, the universe might have collapsed from a previous phase, rebounded, and expanded again. In this picture, the Big Bang was not a beginning, but a transition. One bounce in an eternal cycle. Such models address the problem of initial conditions. If our universe is just one stage in an endless rhythm of contraction and expansion, then perhaps the cosmos needs no ultimate first cause. Closely related are cyclic universe theories, which envision a repeating pattern of birth, growth, collapse, and rebirth. Ancient cultures often imagined time as a cycle. Modern cosmology, guided by quantum gravity, may be converging on a similar idea. The ekpyrotic model, inspired by string theory, imagines our universe as a three-dimensional brain, colliding with another brain in higher dimensional space. Each collision ignites a Big Bang, sending energy cascading into matter and radiation. In this view, our universe is not a lone firework, but one spark among many in a grand, multi-dimensional display. Then there is the most provocative possibility of all, the multiverse. Inflation itself may imply it. Once it starts, inflation may not stop everywhere at once. Some regions may continue inflating while others form bubble universes, each with its own laws of physics. Our cosmos would be just one bubble in an infinite froth, part of an ever-growing cosmic foam. The multiverse idea is controversial. Critics argue it is untestable, beyond the reach of experiment. Yet its logic is seductive. If quantum fluctuations during inflation are inevitable, then countless universes may have bloomed beyond our horizon. Some may be empty, some filled with stars, some with laws of physics utterly alien to ours. Quantum cosmology pushes even further. Some models suggest that the universe itself may have tunneled into existence from nothing, in the quantum sense, not absolute emptiness, but a seething sea of possibilities. In this view, time and space are emergent, springing from quantum rules beyond our classical imagination. Asking what happened before may be like asking what's north of the North Pole. The question itself dissolves. These speculative models remind us of the limits of knowledge. Planck, WMAP, and the CMB can take us back 13.8 billion years to when the universe was a hot plasma. Inflation pushes us further, into the first sliver of a second. But beyond that, we're in a frontier where science shades into philosophy, and where ideas like bouncing universes or multiverses hover between testable theory and metaphysical vision. What unites them all is the drive to understand the origin of time itself. Whether through inflation's quantum seeds, a cosmic bounce, or an eternal multiverse, cosmology today is wrestling not just with how the universe expanded, but with why there is something rather than nothing. When the James Webb Space Telescope, JWST, opened its golden eye in 2022, its mission was clear: to peer deeper into cosmic history than any telescope before it. Webb's infrared vision allows it to cut through cosmic dust and to see light stretched by the expansion of the universe. light that began its journey when the first galaxies ignited. What Webb has revealed so far is both breathtaking and puzzling. Within months of its first deep-field images, astronomers began reporting galaxies that seemed too large, too luminous, and too mature for their early era. Some appeared to exist only 300 to 400 million years after the Big Bang, when, according to standard models, galaxies should still have been fragile collections of stars. These impossible galaxies made headlines, sparking debates about whether our models of cosmic structure formation, rooted in the seeds laid down by inflation, need adjusting. At the heart of the matter is this: inflation predicts a very specific distribution of primordial fluctuations. These fluctuations, stretched from quantum scales, determine where and when galaxies form. If galaxies appear earlier or more massive than expected, it could mean either that our astrophysical models of star formation need refining, or that something about those initial conditions is off. Most cosmologists lean toward the first explanation. Perhaps stars formed more efficiently in the early universe than we thought. Or perhaps dust made galaxies look older than they really are. Yet the tension remains tantalizing. If inflation's predictions about the spectrum of fluctuations were wrong, it would be revolutionary. Webb, in its quiet way, has become a test of the very physics of the first second of time. And it is not just galaxies. JWST is probing the intergalactic medium, the gas between galaxies, during the era of ionization. Its measurements of how galaxies ionize their surroundings provide another test of inflation. Did the early fluctuations produce the right mix of dense and empty regions to allow ionization to proceed on schedule? Every faint smear of light in Webb's images is not just a galaxy, but a data point in the story of cosmic beginnings. For the public, Webb's images are awe-inspiring. Cosmic gardens of spirals, clusters, and arcs of lensed galaxies. For scientists, they are also interrogations of inflation. Do the patterns of structure we see align with seeds planted in a fraction of a second, 13.8 billion years ago? Or are we on the verge of a deeper revision? The universe, it seems, has not finished surprising us. While Webb maps the universe's structures, other experiments are preparing to return to the ultimate canvas, the cosmic microwave background. The Simons Observatory, now under construction in the Atacama Desert of Chile, will begin operations later this decade. Equipped with an array of sensitive detectors, it will measure the CMB's polarization with exquisite precision, pushing deeper into the search for primordial B modes, the faint swirling signature of gravitational waves from inflation. Simons is not alone. The CMB Stage 4 project, CMBS4, planned for the 2030s, will be a massive international collaboration, deploying thousands of detectors across telescopes in Chile and Antarctica. Its goal is nothing less than to settle the question: did inflation produce gravitational waves we can detect? These experiments represent the cutting edge of cosmic archaeology. Unlike Webb, which looks for galaxies hundreds of millions of years after the Big Bang, Simons and CMB S4 aim to probe the universe when it was less than a trillionth of a second old. Their quarry is faint beyond imagining. Ripples in space-time that would have stretched across the cosmos before atoms, before stars, before even light could travel freely. The stakes are high. A detection of primordial B modes would be a smoking gun for inflation, elevating it from the best explanation to confirmed history. It would also open a new window on physics at energies billions of times higher than particle accelerators can reach, providing the first experimental evidence about the unification of forces, or even quantum gravity. Even if the experiments find nothing, the implications will be profound. The absence of B modes would constrain inflationary models, ruling out many versions and perhaps pointing toward alternatives like bouncing universes or cyclic cosmologies. Either way, the cosmos will answer, if not with confirmation, then with guidance. The excitement in the cosmology community is palpable. These instruments represent decades of effort and will gather data on a scale unimaginable to the pioneers of COBE or WMAP, where those early missions painted a portrait of the cosmic sky. Simons and CMBS-4 aim to reveal its brushstrokes, the subtle swirls that may carry the memory of the universe's birth. As we look ahead, it is striking how cosmology has matured. Less than a century ago, the Big Bang itself was controversial. 50 years ago, the CMB was still just static in an antenna. Now we are preparing to test the physics of the first instant of time with laboratories made of sky and ice. The universe, vast as it is, has become our experiment. And with each new telescope and detector, we learn to listen more closely to its whispers. It is easy enough to say, the universe began with the Big Bang. The phrase has become part of our cultural vocabulary, a shorthand for origins. But when we pause to consider what it means, the ground beneath us shifts. What does it mean for time itself to have a beginning? If the Big Bang marks the birth of space and time, can we meaningfully speak of before it? For much of history, humans assumed time was eternal, an endless river flowing from the past into the future. Ancient philosophers debated whether the universe had a beginning or was infinite. Aristotle argued that time had always existed. Christian and Islamic thinkers emphasized creation ex nihilo, from nothing. For centuries, these were matters of theology and philosophy. Science entered the conversation only in the 20th century, when Einstein's equations revealed that time itself could be dynamic, stretching and curving with space. When astronomers discovered that galaxies were rushing apart, the implication was staggering. If we wind the cosmic movie backward, everything converges to a beginning. But that beginning was not a firecracker exploding into pre-existing space. It was the emergence of space and time themselves. The Big Bang was not just an event in time. It was the origin of time. Here the human imagination struggles. Our language is built on before and after, on cause and effect. To say there was no before the Big Bang is to say time itself is bounded, like a road with no stretch, behind the starting line. Some physicists suggest that asking what happened before is like asking what is north of the North Pole. The question dissolves once we realize the coordinate system itself has an edge. Yet inflation complicates the picture. If inflation was real, it pushes us even closer to the origin, into a realm where quantum rules dominate. Some models suggest inflation itself may be eternal, generating universes endlessly, even as our own bubble cooled into stars and galaxies. If so, then time before time may not be a paradox, but an invitation. The possibility that the Big Bang was not absolute beginning, but one episode in a deeper, ongoing story. Modern cosmology lives at the edge of knowability. We can trace the universe back to its first second with astonishing confidence, guided by Planck's baby picture and Webb's glimpses of first galaxies. But beyond that, before light, before atoms, before inflation itself, we face a fog of ignorance. This ignorance is not failure, but frontier. Science has always advanced by pushing the limits of measurement. We could not see bacteria until the microscope was invented, nor the star's spectra until prisms were refined. Today, our microscopes are satellites. Our prisms are radio antennas, frozen into Antarctic ice. Each tool extends our reach, but there will always remain horizons we cannot cross. The cosmic horizon, the maximum distance light has traveled since the Big Bang, is one such boundary. No matter how powerful our telescopes, we cannot see beyond it. Inflation, quantum gravity, multiverses, these lie outside direct observation. But they do not lie beyond imagination or mathematics. By building models consistent with the evidence we do have, and by devising ever more ingenious ways of testing them, cosmology edges closer to truths about the unseeable. In this sense, the time before time is not a contradiction, but a challenge. It is a reminder that science is a human endeavor, forever caught between what we can measure and what we can only wonder. The search for the beginning of time is more than physics. It is a story about us. Every culture has told origin myths, cosmic eggs, gods splitting chaos into order, worlds born from rivers or fire. These stories express something essential: the need to know where we came from. Modern cosmology is the latest chapter in that ancient quest. When Planck mapped the CMB, when Bicep 2 scoured the sky for ripples, when Webb revealed the first galaxies, they were all answering the same question our ancestors asked beneath the stars. How did it all begin? The difference is that we now use satellites instead of stories, equations instead of epics. Yet the awe is the same. Inflation, multiverses, bouncing models. These may sound abstract, but they speak to the deepest mysteries of existence. Why is there something rather than nothing? Why is the universe comprehensible at all? Why does it produce beings like us, capable of asking the question? In seeking answers, cosmology does more than describe the universe. It gives us a mirror in which to see ourselves. What lies ahead is both thrilling and uncertain. The Simons Observatory and CMB-S4 will probe inflation's signature with unprecedented sensitivity. If they detect primordial gravitational waves, it will be one of the greatest scientific triumphs of all time. Direct evidence of physics at energies 1 trillion times beyond Earth's accelerators. If they do not, the story will not end. Instead, new models will rise. New possibilities for quantum cosmology will emerge. Perhaps bouncing universes will gain traction. Perhaps modified theories of inflation will replace the simplest versions. Science thrives not on certainty, but on correction, on being surprised. The real future, though, is in synthesis. Webb's galaxies, Simon's polarizations, SKA's mapping of cosmic hydrogen. Together they will weave a narrative of the universe's first billion years. For the first time, we may see the chain unbroken. Quantum jitters stretched by inflation, grown into filaments of the cosmic web, lit by galaxies, and eventually producing beings who gaze back. To describe the universe's beginning is to speak in poetry as much as in physics. Inflation is mathematics, but it is also metaphor. A moment when nothing became something, when the void blossomed into a cosmos. The cosmic microwave background is numbers on a graph, but it is also a baby picture, a first family portrait of reality. We live in a universe that leaves traces of its own birth, like fossils in stone. We are creatures who can read those traces, who can see in faint microwaves the echo of time itself. This fact alone is staggering. In a universe of dark matter and dark energy, of billions of galaxies and trillions of stars, we exist as a species capable of wondering not just how, but why. When we speak of time before time, we are speaking as much about human imagination as about physics. It is the imagination that dares to picture a bounce, a multiverse, a quantum sea of possibilities. It is the imagination that builds telescopes in deserts and on mountaintops to glimpse the invisible. Science is not opposed to wonder. It is wonder disciplined into discovery. In the end, all our cosmological maps converge on one truth. The first second of the universe holds the key. Inflation, if it happened, transformed a quantum flicker into the grand structure of galaxies. The CMB froze its echoes into light. The first galaxies, now visible with Webb, tested those echoes against reality. To study that first second is to study the origin of everything we know. And yet beyond it we confront mystery. Perhaps the Big Bang was the beginning. Perhaps it was one bounce in an eternal cycle. Perhaps ours is one bubble in a vast multiverse. We may never know. But the pursuit itself is part of what it means to be human, to reach beyond horizons, to wonder what lies before beginnings, time before time. The phrase may seem impossible, but in chasing its meaning we glimpse something profound, that the universe, vast and ancient, is not only a place we inhabit, but a story we tell. And in that story, the first chapter is still being written, in microwaves from the sky, in galaxies at the edge of sight, in equations on chalkboards, and in the unquenchable curiosity of beings who dare to ask, how did it all begin?